I'm very excited to start this week off. I'm looking forward to the whole week. I'm especially looking forward to being done with the talk and enjoying the rest of the week. So yeah, I'm very happy with what's about to happen. So I'm talking about Borel asymptotic dimension and hyperfiniteness. And this is a sort of a project that's been going on for a while. And I want to give some background to sort of put various descriptive set theoretic questions about complexity of equivalence relations in a unified context of sort of understanding Borel proper metrics. But before I begin, I want to mention that this is all joint work with Steve Jackson, Andrew Marks, who's in the audience, Brandon Seward, and Robin Tucker-Drob, who's also in the audience. Oh, and let me do this before I violate the rules. Okay. So the setup is as follows. So throughout, capital X will be a standard Borel space. So just think of this as a Polish space equipped with its sigma algebra of Borel sets. And rho will be a function from pairs in X to sort of the extended non-negative real numbers. This will be a Borel extended metric. So what I mean by extended metric is that the distance infinity is allowed, right? But it satisfies the usual axioms of being a metric, and moreover, it's Borel as a function between these two Borel spaces. So when you have this data, this induces for each real number, I'll say less than infinity, a Borel graph denote it by GR on X, where 2 points are going to be adjacent. If they're distinct, but kind of close together. Right? So you think of this as a notion of proximity. And indeed, because metrics are symmetric, this will be a graph for free. Right? And also, I knew I was going to do that. Okay. We also obtain a Borel equivalence relation For a moment, I thought I was getting taller. Okay. Just unioning up these graphs, right? So this equivalence relation, 2 points will be equivalent if they're a finite distance from one another, right? And it's not so hard to check that this is a Borel equivalence relation. Good so far? So we say that such a Borel extended metric rho is proper if for every x, for every r, the ball, I'm not going to define this, doesn't really matter. So I want every ball to be finite, right? So I say no matter what base point I pick and what radius I pick around that ball, there are only finitely many y's within distance r of x. Okay. And so you can view this as having sort of a graph theoretic analog. This rho being proper sort of is the same, I'll write like this, as every one of these things being, each one of these is locally finite, in the sense that every vertex has only finitely many neighbors. And also, rho being proper implies that this corresponding equivalence relation is a countable Borel equivalence relation, which means every equivalence class is countable. Right? Okay. Make sense? So before embarking on this journey, I want to give some examples of this setup, because it turns out that this language of sort of looking at these finite distance equivalence relations for Borel proper metrics generalize a lot of equivalence relations commonly considered in this corner of descriptive set theory. So, well, this example is kind of clear. I'll use a slightly different G. So if G is a locally finite Borel graph, that is, if you start with one of these graphs, you can sort of reconstruct a metric out of it that looks very similar to this. Then the graph metric is proper Borel extended metric. And of course, the corresponding equivalence relation is the connectedness relation. Right, so by a graph metric, I mean the length of the shortest path between two vertices. And two things are connected if there is a path between them. Right? And so if they're of infinite distance, that means they're not in the same connected component of the graph. Slightly more interesting example. So if gamma is a countable group, oh, and I should mention, of course, in this case, when you start looking at the GRs over here, these give the various powers of this graph G, like you're within a certain distance of one another, right? Okay. So if now gamma is a countable group with some fixed right invariant metric proper metric D, as usual, if we have a structure on a group and we have a free action of that group on a space, we can sort of translate the structure from the group to the space upon which it acts. So we may associate with each free Borel action so gamma is acting on some standard Borel space by Borel automorphisms, and moreover it's free in the sense that points have trivial stabilizer. So we associate with each of these metric rho by the following. So the distance between 2 points is sort of, you look at how far the group element that sends one to the other is from the identity in this metric on the group. And well, if that exists, it's unique by freeness. And so this is unambiguous. And if that doesn't exist, well, then we declare the distance to be infinity. And so and then in this case, the E rho is just the orbit equivalence relation. Of this action, right? Because 2 points will be a finite distance exactly when there's a group element which sends one to the other. And right invariance is important. That ends up being the correct invariance so that this works. I'll let you grind through the details, but it's not so hard. Okay. And so an important remark, the reason that we set things up like this in B is because a lot of this theory, especially about sort of analyzing descriptive complexity of free actions of groups, specializes to finitely generated groups. Exactly because locally finite graphs have certain nice properties, and it's nice to have a degree bound and so on. But this notion makes perfectly good sense for non-finitely generated countable groups as well. And it's because every countable group, I mean, this is an easy exercise, admits a proper right invariant metric. So by using this metric language, instead of just saying, okay, I fix a finite generating set and look at the corresponding Cayley graphing, you can actually handle sort of infinitely generated groups as well. And this is more than just a superficial transformation, right? A lot of issues, a lot of roadblocks in this area came from sort of understanding finitely generated groups and then writing arbitrary groups as unions of these finitely generated subgroups and trying to sort of conclude something about the structure of this union object. But it turns out that unions of this type play very poorly with, well, as far as we know, hyperfiniteness, as I'm about to discuss. So by just allowing yourself this little bit of flexibility, it really cleans up a lot of the theory. Okay. Good so far? And so the central question that we want to address is how do we connect properties of this metric space, or this extended metric space, to properties of the associated equivalence relation. And so one particularly important property of an equivalence relation was hinted at the title of the talk, so I'll define it right here. So again, when I write CBER, I mean a countable Borel equivalence relation. So a Borel equivalence relation, all of whose classes are countable. So we say that such an equivalence relation is hyperfinite if is an increasing union of F-burs, which I also haven't defined, but I bet many of you can guess what it means. So F means finite. So an F-bur is a Borel equivalence relation, all of whose classes are finite. Right? So maybe more explicitly, so there exist finite Borel equivalence relations that are getting coarser and coarser. And they union up to E. Right? So in other words, E can be approximated in some uniform sense very well by finite Borel equivalence relations. Or the way I sort of think about this is as you increase the index n, as these equivalence relations are getting coarser and coarser, you're sort of merging classes together, right? So as you advance n, your equivalence classes are sort of getting stuck together, but they're always finite along the way until at the very end, at stage omega, or when you run through all the natural numbers, they've coalesced to be exactly the E classes. And so this notion of hyperfiniteness has been of critical importance in the study of Borel equivalence relations. It's sort of the first level of this hierarchy, which is in some sense genuinely non-trivial. And there are a lot of open questions about which equivalence relations are hyperfinite or not hyperfinite. What sort of closure properties does the class of hyperfinite equivalence relations have? To what extent do measures detect hyperfiniteness, and so on? There's just, I mean, we've been studying hyperfiniteness for a while, and we're still awfully ignorant about it, in my opinion, despite it being sort of the simplest class of non-trivial equivalence relations. And so we want to sort of connect, ideally, make a connection of this sort that helps us establish hyperfiniteness of various equivalence relations. And indeed, that's where we're going. And as you may have guessed from the title, there's a particular metric property that's going to be useful. And that's my next job, is to define that. So first, let me just, to remove all doubt, let me define some terminology that will allow me to be lazy. So given a bunch of subsets of X, we say that this family is uniformly bounded if there exists some real number r, I'll call it big R, because it's supposed to be big. So there's some bound on all of the diameters of all the sets in this family. And so, but the diameter of a set is just the soup of the distances between points in that set. Good? Okay. So I'm trying to decide if I can squeeze the critical definition here. I'll try. So this will be the definition of Borel asymptotic dimension. So this definition is going to generalize a definition due to Gromov, sort of in studying metric, sort of this, this idea of studying groups from this metric perspective and taking these sort of asymptotic properties of groups and using that to inform you of the structure of the group and so on. And basically, we're just taking one of the millions of equivalent definitions of asymptotic dimension and putting the word Borel in strategic places and hoping that it'll be a useful notion. And so since it's in my talk, I'm going to pick my favorite of the equivalence definitions and declare that that's the official definition without further ado. So given one of these proper Borel extended metrics that we've been talking about, I'll just write this because this is the official definition. So given this configuration and some natural number s, we say that the Borel asymptotic dimension of this proper Borel extended metric is at most s if r greater than 0, there exists a Borel partition my indexing is correct here. I mean a partition into s plus 1 many pieces, such that for all I, the connected components of this distance r graph that I defined right over there, the restriction to this set Wi, these connected components are uniformly bounded. I'll draw a picture in a second. I know that there's a lot going on in this definition. Okay, so the idea is your opponent hands you a radius r, or a scale r to work against. And so this r is going to determine this graph gr at the end that you're trying to sort of fragment into finite pieces, right? So your opponent hands you this r. Your job is, given this r, to chop up your space into s plus 1 many Borel pieces, such that when you restrict this graph gr to each of these pieces, not only are all the components of that restricted graph finite, not only have you fragmented them, but they're in fact very finite, right? They're of bounded size, kind of. Right? They're of bounded diameter. So it's somehow stronger than chopping into finite connected components.
In the beginning of the definition, you don't have the graph. Like you were attaching the graph to the metric row.
All I have is a metric.
Could you repeat the question?
Oh, yes. The question was, at the beginning of the definition, I don't have a graph. And the answer is yes, I don't have a graph. This is just a property of the metric row. Of course, in practice, this metric row is often coming from a graph or coming from something.
Well, you have the graph in the end of the definition.
Oh, we have the GR.
Yeah, well, I have, given a metric, I naturally induces a parameterized family of graphs. But yeah, you're sort of, the name of the game is you have to think about all of those graphs, kind of, right? It's not just a single graph. Okay, and so at first glance, this probably doesn't even look like a notion of dimension at all, right? I mean, like, what is so dimensional about this? So let me first draw a picture of something of dimension 2, right? So here's a typical where by picture, I mean, it's going to look like a plane, and planes should be two-dimensional, right? Okay, so a familiar definition of dimension in this kind of context from topology, let's say, something like covering dimension or so on, right? So we have a good example over there. So if you look at that wall, the tiles of that wall prove that the wall is two-dimensional, right? So let me or at most two-dimensional. So let me copy that picture. So we have something like, and then you also have some stuff coming off of here, stuff coming off of here. Okay, right. So often when you think of proving something has some sort of topological dimension 2, you want to say something like, at an arbitrary scale, I can chop up the space into finite regions such that each point is near at most d plus 1 of the regions, right? So 2 plus 1 equals 3. So this type of configuration, since I can do it at arbitrary scales, proves that the chalkboard is two-dimensional in some sense, right? Do you see what I mean? This usual notion of covering dimension says something like, whenever you have a little scale r, you can tile the space or cover the space by open sets or something like this, such that each point is near at most d plus 1 of the pieces, right? No, this is not in 3 pieces. This is just, no, so the usual way dimension is realized is like there exists a cover of the space such that each point is within distance r of at most 3 elements of the cover, right? But now I'm about to convert this into this definition. Okay, so how do we convert that to something that looks like this? Well, we build this picture out of gumdrops and toothpicks, right? So we put a gumdrop around each of these intersection points. You get the point. I'm not going to do all of them. So these are going to be W0. And now I put toothpicks between the gumdrops. I missed a gumdrop over there. And over there. And then finally, although I never got this far in my gumdrop and toothpick configurations, these faces you fill in, and they'll be W2, right? So as long as you choose these parameters, and maybe R is something on the order of this for a sense of scale. So R is something very small to this compared to this. So let's investigate each of these regions in turn, right? So W0, these red regions, as long as these gumdrops are relatively far apart from one another, you can't jump from one gumdrop to another gumdrop, right? So the connected components of this distance R graph will be trapped inside these gumdrops, right? So they'll be uniformly bounded by whatever the diameter of these gumdrops is. Okay, now let's look at the toothpicks, W1. So if I now look at these toothpicks, I just need to rule out being able to jump from this toothpick to another toothpick, right? And I can do that by making the gumdrops big enough, right? So as long as I make the gumdrops big enough to prevent my ability to jump from this toothpick to this toothpick, I have then finitized W1. And again, I can make all this uniform, at least uniformly bounded. And finally, if I look at the W2 components, as long as I make the toothpicks thick enough and the gumdrops thick enough to prevent a jump like that, I finitize the W2 components. Does this make sense? Okay. And indeed, in general, given one of your covering definitions of dimension, you can convert it into an instance of this by saying, okay, are your points near like 3 elements of your cover? Are your points not near 3 elements of your cover, but near 2 elements of your cover? And so on. So this not only gives you sort of a typical picture in dimension 2, but also if you think about a little bit, converts sort of covering dimension into this type of dimension. Does this picture sort of make sense? Okay. I know I'm not being super precise, but the whole point of a picture is to not be super precise.
Is there an easy way to see that the board is not one-dimensional?
No. I mean, kind of, but I wrote this because I didn't want to answer that question. I mean, it's not the hardest thing in the world, but it would take too long. Okay. So the upshot is that these notions are indeed connected. So suppose we have some natural number, and we have one of these proper Borel extended metrics. Yes.
I have a nice question. Wouldn't it work if you just colored each of the bricks in 3 colors in a periodic way?
Yes, but that wouldn't generalize. There are subtle issues with doing that. So I did this, but I was hoping somebody would ask that question. Yeah, it would work. You could do it here, but that proof doesn't generalize in the same way that this one does to arbitrary covers. Excellent question. All right, so suppose we have one of these situations, and of course in this picture I'm also glossing over things being Borel and so on, but if you can do one picture in a Borel way, you can definitely do the other picture in a Borel way. Okay, so suppose that we have this situation. So we have a proper Borel extended metric whose asymptotic dimension is finite. Well, then we already know that the induced equivalence relation has countable classes. I mentioned that up there. So it's of the right type of object to be hyperfinite. And it turns out it is hyperfinite. So having finite asymptotic dimension just outright implies hyperfiniteness of the corresponding finite distance equivalence relation. And so I will sketch a proof of this, literally. Now that I know for sure that I have colored chalk, I feel like I'm allowed to just draw pictures instead of prove things. So the idea is for each R, for each parameter R in the definition of Borel asymptotic dimension, we get a Borel partition I guess I'll just put some R's up here. So we can partition the space so that the corresponding definition works at that level R, right? And what we want to do is we want to use all of this information to somehow build a witness to hyperfiniteness. So the intuitive idea is that we fix the other one, the index, and vary R to build finite Borel equivalence relations, witnessing, and I'll put this in quotation marks so it's not exactly true, hyperfiniteness. And I'll explain the quotation marks in a second. Okay, but first let me doodle the picture before I get into the details. Okay, so because the only thing I know how to do in mathematics is color graphs, I think of, whenever I say a partition, in my brain what I'm thinking is color the space, right? So I can think of these as like the red points, these as the blue points, and so on. So I have this coloring of my points for each scale R. And I want to somehow say, okay, I look at the red points of all scales, I want to use those to build something. I look at the blue points of all scales, I want to use those to build something, and so on, right? So well, so let's focus on red points. That is the corresponding W0. So I'm not going to draw them in red because everything will be the same color. OK, so at stage, let's say r equals 1. What does the picture look like? The red points will be a bunch of finite blobs. Maybe I'll color them in red just to indicate that they're red. OK, and these blobs are uniformly bounded in size, but they're also relatively far apart from one another. So in this case, they're at least distance 1 from one another because r0 is 1. And they also have some uniform bound on their size, right? So that will be big R0. So I take that big R0 and plug it in as R1 in my definition, and I get something else, right? So, sorry, I'm thinking about how faithfully I can enact this picture. So these are the blobs at the previous level. And now on top of these blobs, I have big blobs. Maybe here's one. And maybe here's one. And so these points are red. Red, 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 red. But because I know that the big blobs are distance r0, are big r0 apart from one another, each little blob can intersect at most one big blob, right? You can't have another big blob right here, because that would mean these two blobs are too close together, right? And so what I do now is I take these sort of amalgamated blobs, and this will be a typical F1 class, right? And so indeed, F1 is a bigger finite equivalence relation than F0. And moreover, I now have a bound on the size of these blobs. So big R1 sort of bounds the diameter of these amalgamated blobs. It's something like twice this diameter plus this diameter, or something like that, right? So you get some bound on big R1. And you keep doing this, right? You iterate the process. You then, at the next stage, you take that big bound to build even bigger blobs. Each of these bigger blobs can only meet, each of these scale blobs can meet at most one of the bigger blobs because they're so far apart from one another. This gives you a yet coarser equivalence relation and so on, right? And so these equivalence relations for each color will union up to something hyperfinite, right? Whatever they are, it will be an increasing union of finite equivalence relations. And so their union will be hyperfinite. And now the trick so in this fashion, so you obtain for each of these colors a hyperfinite equivalence relation contained in E row, right? And then the final step, and I'm not going to go over the details of this because it's not that interesting, is that you can argue that each E row class contains at most one class of each of the colors, right? And so this, with a tiny bit of work, that E row is finite, in fact, sort of S plus 1, index above a hyperfinite thus hyperfinite. So one of the few closure properties we actually do know about hyperfinite equivalence relations is that if you have a big hyperfinite equivalence relation and a subequivalence relation, if you have a big equivalence relation E, a subequivalence relation F, which is hyperfinite, and each E class contains at most finitely many F classes, then E is also hyperfinite. I usually assign that in homework in my descriptive set theory classes. It's a good exercise. So that's the proof, right? So the idea is in each color, you do this blobby amalgamation process to say that the red points think that the equivalence relation is hyperfinite, the blue points think the equivalence relation is hyperfinite, the green points think the equivalence relation is hyperfinite. Altogether, there are only finitely many colors, so altogether the whole equivalence relation must be hyperfinite. Does the intuition make sense? Okay. So we have a theorem, so let's try to use it for something. I wonder if I can push both at once. Nope.
The third one.
Yeah, it stops everything. Yeah, and I don't want to use the third board because I'll just get confused. Okay.
Gamer, you can use the German tool.
No. I can't even use a third board. There's no way I could use that. Yeah, that's a good way for me to slip and fall somehow. Okay. Does at least the construction sort of make sense, how I'm coarsening these equivalence relations? That's the big point. And so it's convenient to have this type of theorem because in practice, establishing hyperfiniteness means you have to build sort of an entire coherent sequence of equivalence relations performing some task. And it's usually a huge pain to do that. And the nice thing about this finite asymptotic dimension terminology is you just need to say that sort of for each parameter, you can build a corresponding object. But these objects don't need to cohere in any particular sense, right? It somehow localizes the problem to say, you give me an R, I give you a partition. And I don't need to make sure that these things refine one another or so on. This sort of meta argument takes care of all that nonsense. So it compartmentalizes the question to just sort of answering a finite question, kind of. So how are we going to apply this? So a long-standing question, which I'll paraphrase. So Benji Weiss asked this. Asks to classify those countable groups such that every Borel action has hyperfinite orbit equivalence relation. So this is sort of a Borel dynamics version question, sort of corresponding to traditional amenability stuff in the ergodic theoretic context, right? So there's these theorems of Ornstein-Weiss and Kohn-Feldman-Weiss that say in the measure theoretic category, when you have actions of countable groups, they sort of correspond to actions of Z, let's say they're free, measure preserving, if and only if the acting group is amenable, right? And so this is some sort of, now let's remove the measure from the picture. To what extent does that remain true? So certainly those groups which have only hyperfinite actions are going to be a subclass of the amenable groups, but it's unclear whether that subclass equals all of the amenable groups, or maybe there's some special amenable groups that have this property and some others that don't, and so on. And so example B that I erased, I think I just erased it because I can see the B. Example B allows us to rephrase this question for free actions or maybe not, maybe rephrase is the bad word, but ask a variant question in the language of asymptotic dimension. Because asymptotic dimension, or Borel asymptotic dimension, let me put a B down here, gives us a sufficient condition for hyperfiniteness. So if we want to prove that a group has all, let's say, free Borel actions have hyperfinite orbital equivalence relations, it would suffice using this example B terminology to prove that the corresponding Borel extended metric had finite asymptotic dimension. Because we know that finite asymptotic dimension implies hyperfiniteness. And so let me rewrite sort of example B. Let me rewrite the definition of asymptotic dimension in a language that looks more group theoretic, because I know that there are some people in the audience that maybe don't like metrics in this sense. So the action, let's say the free action, has asymptotic dimension. And of course, when I say the action has asymptotic dimension less than or equal to S, I mean the corresponding thing in example B. And it's going to be independent of this, like most asymptotic properties. The actual metric you pick on the group won't matter. Okay, so this action has asymptotic dimension at most S, if and only if, for all finite subsets of gamma, there's a Borel partition. Into S plus 1 many pieces, and another finite subset of gamma. So your opponent hands you A, you have to cook up the partition and B such that for every point, for every index, I'm going to use some undefined terminology or notation and then define it in a second. Okay, so I'll define that in a second. Just want to move the board up. Okay. So GA is the graph connecting x to s dot x. Maybe I shouldn't use s, a dot x. Right. So given a finite subset of a group, you can just say two things are connected to one another if something in my set moves one to the other. And let's subtract the diagonal. Let's assume that we don't have to worry about loops or whatever. And this notation is the connected component. I'm trying this. I just made up this notation. I'm trying it to see if I like it. Because it's always a huge pain to talk about connected components of vertices in proper language. So if we just abuse notation a little bit and pretend like it's that. So the idea is, instead of talking about metric parameters, instead of saying I have my graph G sub R, where R is a distance, and I'm looking for big R uniformly bounding things, doing that sort of metric analysis is the same as saying, given any finite subset of the group, I can cook up a bigger finite subset witnessing the uniform boundedness. And I'll leave it as an exercise to check that these are literally equivalent for proper metrics on groups. So this looks less metric somehow. And in practice, this is often how things go. You imagine sort of your opponent hands you some finite subset of the group. This gives you a graph, and your job is to fragment the graph into finite pieces. Okay. Well, into bounded pieces. Are there any questions about this? How long do I have?
4 minutes.
Oh. Okay. Yeah, I know. It's a common mistake. Easier to ask for forgiveness. Okay, so let me do some examples. So if I look at locally finite groups, so all free Borel actions actually have asymptotic dimension 0, right? Why is this the case? So if I'm going to witness asymptotic dimension 0, that doesn't give me too many options about which partition to use, right? The only thing I have is W0 equals X. But that verifies this, right? So if your group is locally finite, then subgroups generated by finite sets are finite. And if you connect a bunch of A edges at a point X, you're not going to be able to leave the orbit of this group. So this example. So if I look at finitely generated groups of polynomial growth, again, all free Borel actions have a finite asymptotic dimension. And indeed, you can, the asymptotic dimension has something to do with the degree of growth of the graph, or of the group. And at least in the context of finitely generated groups, this was essentially all that was known for a while about what properties of groups imply that all of their free Borel actions are hyperfinite. There was work, important work of Gao and Jackson, and later of Seward and Scott Schneider, sort of generalizing these to various non-finitely generated groups. But as I mentioned at the beginning, this involved this very annoying diagonalization procedure because we don't know whether increasing unions of hyperfinite equivalence relations are hyperfinite. So one sort of side bonus of this asymptotic dimension machinery is it makes that sort of diagonalization easy, but I don't want to talk about that in my remaining 1 minute. So, but there are also some new examples. So every free Borel action of this lamplighter group has asymptotic dimension equal to 1. I was hoping to sketch an argument of this, but I have no time. So maybe if people are interested, maybe we can have some chat later where I sketch a proof of this. But this in particular is the first known example of a finitely generated group of exponential growth, all of whose free Borel actions are hyperfinite, or the first of a class of examples. And then more generally, sort of groups admitting a normal series. I'm going to be super vague here because I have no time to explain this. So there's a sense in which what you'd want, for example, if you'd want to show that every elementarily amenable group has a hyperfinite orbital equivalence relation, you'd want some procedure saying okay, if I have a nice group and I extend it by Z or I extend it by something, then the resulting extension will also have the nice property. So it'd be nice to have some technology that allows you to advance through some normal series witnessing like for instance, solvability of the group or something. We don't quite have that, at least not yet, although maybe recent advances of David Kerr and Peter Narishkin might help us analyze that. But for now, we don't quite know sort of in general how to handle those extensions. But if they're nice successive quotients that have certain packing properties that I'm not going to have time to discuss, then we can do it. So for example, polycyclic groups we can handle in this language. But the one thing I want to close with is that even if all you care about are finitely generated groups, and I know that finitely generated groups have a sort of important role in this story, if you think about, for example, the lamplighter, there's no reasonable way, at least that I know of analyzing the lamplighter, which is a finitely generated group, without also analyzing the sort of canonical normal subgroup, which is the free abelian group generated by countably many involutions that sort of sits inside the lamplighter, right? And so in order to analyze this finitely generated group, you're going to have some process of analyzing non-finitely generated groups along the way, right? How else are you going to analyze the lamplighter without analyzing the thing that the Z acts on, right? And so in general, liberating your mindset from only worrying about finitely generated groups, and this is something that asymptotic dimension allows you to do, I think is useful also for analyzing finitely generated groups. And that's it.
Other questions?
Does your D plus include the groups that are located aligned by Z, so generally C?
Not quite. I don't think, not quite. I'd have to think about it. So certainly, like, if you have something like this, no, not quite. I don't see an argument. This uses very special properties of the action of Z on this particular group, because you know that when you translate one of these cylinders, you know sort of exactly how many other cylinders you can intersect and so on. And I could imagine locally finite by Z groups that don't have that property.
And what about metadelium? Locally finite by Z and metadelium?
I think even then, I'm not willing to claim it, yeah.
Other questions?
Is there an example for converts, like the hyperfinite with infinite?
Yeah, so for example, if you look at the group generated by, like Z to the less than omega, right? So Z to the less than omega is an abelian group, so by Gauss-Jackson, its orbit equivalence relations will all be hyperfinite, but it has infinite asymptotic dimension. And indeed, one of the big questions that's on my mind is whether you can replace this with Z-Reth Z. Like whether Z-Reth Z is hyperfinite seems to be a very important special case of this whole story.
Do you have a deep belief about the long-standing question? Amenable groups?
I'm more likely to believe that elementarily amenable groups have hyperfinite orbit equivalence relations, and I'm really suspicious of other groups. I mean, I'm not going to claim that in public while being recorded, but
Other questions?
Okay, so I assume the free group is dimension 1.
it has real dimension 1, but it has Borel dimension infinity.
Correct. But so how about an amenable group that has finite is inclusive dimension? This is a metric space.
Sorry, the question is whether those things should give you hyperfinite equivalence relations. Who knows? Yeah. I agree that makes sense as a question. But like I said, we're already having issues with certain extensions by Z. So like, in real life, extending by Z just doesn't do much to your dimension, like adds 1 or something, right? But in this context, it seems to be a big difficulty. Yeah.
Residually finite amenable helps?
Maybe? I don't know. I mean, this whole thing is a wilderness, right? It's hard for me to, I mean, I don't see a way in which it helps. But maybe I'm missing something obvious.
The question is about residually finite?
Yeah, whether if you restrict your attention to residually finite groups, does maybe this question become easier?
I guess the motivation being that we know they're monotile. Was that the sort of the
Yeah.
Okay.
Yeah, I mean, like I said, sort of this extension by z question is already really hard, right? And